So we've been doing operations on vectors for a while. So let's take a look. We know that we can add two vectors or subtract vectors. We know that we can multiply a vector by a scalar. But now I'm going to introduce a new operation called the dot product. And let's just look right at an example. If I have two vectors u and v, and I want to perform this new operation called the dot product. Well, if I told you that the dot product winds up giving you a number, in this case 14, could you figure out where we got 14 from? You might want to hit pause and see if you can figure this out. Okay, so where did we get 14 from? Well, it turns out that if we multiply the x components and we multiply the y components and add those together, we get a value which is this dot product value, which will give us 14. So in other words, we do 4 times 5 plus negative 3 times 2, and that gives us 20 plus negative 6, which is 14. And so that's the dot product. So it's the sum of the product of the corresponding components. Let me say that again. Just kidding. It's the sum of the product of the corresponding components. In notational form, we could write it this way. With vectors u and v, it's going to be u sub x times v sub x plus u sub y times v sub y. And that's it. So that's this new dot product. Now we're going to spend some time figuring out how that's useful. But first of all, let's practice this. If I give you two vectors s and t, find their dot product. Once again, hit pause, calculate your answer, and then see if you got it right. Notice these two vectors are in ij form, where I and j are those unit vectors, 1, 0, and 0, 1. But it's still the same idea. Pick out the x components, so s dot t is going to be negative 3, and I shouldn't use a dot because that's confusing. So negative 3 times 7 plus, multiply the y components, 4 times negative 1. And we get negative 21 plus negative 4, negative 25. Easy enough calculation. Everybody should be able to do that. Let's look at some other examples. Find the dot product of these two. Well, negative 1 times 2 is a negative 2, plus a negative 28 is a negative 30. Why did I have you do another one? Well, let's look at this one. Do the dot product of 2, negative 7 with the vector negative 1, 4. Once again, negative 2, negative 28, we're going to get negative 30. So what does that tell you? Well, the order that we do the dot product of two vectors doesn't matter, so the dot product is commutative. And that makes sense because the calculations we have to do to get the dot product are what? Addition and multiplication. And those two operations under the real number system are commutative, so it would make sense that the dot product is also going to be commutative. What else? What if we did this calculation? What if we did the dot product of a vector with itself? What's going to happen? Well, we're going to do negative 1 times negative 1, or negative 1 squared, and then 4 times 4, or 4 squared. So we're going to get 17. Now, do those calculations remind you of something? When did we do that before? How did we find this? How did we find the magnitude of a vector? Well, didn't we do the square root of the x components squared? X component squared plus the y component squared? That's exactly what we're doing here, except we're not taking the square root of it. So what that means is that when you do the dot product of a vector with itself, you get the magnitude of the vector squared. So the dot product of a vector with itself gives you the magnitude of the vector squared. All right, let's kick it up a notch. What if we have these three vectors? I want you to do two calculations. And go ahead and hit pause while you work these out. All right, let's do the first one. We have vector A dot, and this is where, I'll draw an arrow here. As we start to do more calculations, it's important to understand before you even start what kind of answers you're getting. So here, I'm adding two vectors. A vector plus a vector gives me another vector. And then I'm doing the dot product of two vectors, and I'm going to get a number or a scalar. In this calculation, I'm doing the dot product of two vectors, which is going to give me a number or a scalar. And then I'm doing the dot product with two other vectors and get another scalar. And then I'm adding those two numbers together, and I'm going to get a number for an answer. So in both cases, we're getting a number for an answer. So let's see what happens. So vector A, which is 1, 3, I'm going to do the dot product of, and I'm going to add vectors B and C together. Well, that's going to give me what? 2, and then 2 plus negative 1 is 1. And now do the dot product, 1 times 2 plus 3 times 1, and that should give me 5. Okay, let's do this other calculation. Let's do the dot product of A and B. Well, that's going to be 1 times negative 2, those are the x components, plus 3 times 2, those are the y components. All right, so that's A dot B. And now let's do A dot C. That's 1 times 4. And then the y components, 3 and negative 1. Multiply those together. And what are we going to get? Negative 2 plus 6, we're going to get a 4. And here we'll get 4 minus 3 is 1. And lo and behold, we get the same answer. So you might have guessed that that would happen. But remember, we're dealing with vectors, not numbers. So normally you would look and say, oh, the distributive property would apply here. But with vectors, that seems like a totally different animal. But it turns out that we can distribute, in a sense, with vectors this dot product and do A dot B and then plus A dot C, because we wind up getting the same answers. Now, just because it worked for this one case doesn't mean it works all the time. We actually probably should prove that. Let's see if we can prove that. We'll go through a proof rather quickly, but hopefully you can follow along. All right, so I need 3 vectors. So I'm calling my vectors A, B, and C, and A sub x, A sub y for the x and y components, B sub x, B sub y, and C sub x, C sub y. So let's do the left-hand side of this equation. Remember, we don't know if this is true yet. We're trying to prove that. So let me start with the left side and see what I get. A dot B plus C. All right, so the A vector, do the dot product with vectors B plus C. When I add B plus C, I get a vector, and it's going to be the x components added together, comma, and the y components added together. Now let's do the dot product. We multiply the x components, so I'm doing A sub x times, and remember, these are values now. These are values of the vector, components of your vector. And then plus, and then multiply the y components. So A sub y times whatever B sub y plus C sub y equals. And now I'm dealing with numbers here, so I can distribute, because those are operations with the real numbers. And so I wind up getting A sub x times B sub x plus A sub x times C sub x. Plus, and now let's distribute the y component number value. That'll be A sub y times B sub y plus A sub y times C sub y. So that's what I get when I do that those operations. Okay, now let's work the other side. Let's switch colors. Let's do this in blue. I want to do A dot B. So when I do A dot B, I'm going to get A sub x times B sub x plus A sub y times B sub y. And then plus, put these in brackets here. So that's going to give me a value, a number, plus, and now let's do the dot product of A and C. So that's going to be A sub x, C sub x, plus A sub y, C sub y. And these are all values. I'm adding them together, so I can put them in any order we want because addition is associative. So let's say I want to rearrange this, and let's put all the x component values together. So that's that, and then the y's, a sub y, b sub y, and a sub y, c sub y, takes care of those. And this is what I get when I do that. And obviously, these are exactly the same. So now I have proven that this distributive idea or property works with vectors. So that comes in really handy. All right, let's talk about some angles. If theta is an angle between two vectors u and v, it turns out that we have this relationship. I won't go through and prove this one for you, but this is one of the more important relationships to remember about vectors. It's basically telling you that if you have two vectors, you can figure out the angle between them. You simply do the dot product of the vectors and divide that amount by the product of the magnitudes of the individual vectors. And that will equal the cosine of the angle between them. So you can find theta by doing the inverse cosine of that fraction. What would happen if the dot product wound up being 0? Put an arrow here. So before we jump into an example, actually let's jump to an example and we'll come back to this. Let's see, how about, let's do this. Find the angle between these two vectors. All right, so let's write out a formula. The cosine of theta is going to equal the dot product, u dot v, over the magnitude of u times the magnitude of v. So in this case, we're going to have the cosine of theta equals, what's the dot product? 4 times 3 is 12, plus 2 times 5 is 10. And the magnitude of the first vector, 16 square root of 20. Notice I'm not even going to bother trying to simplify that square root, that radical. And then times the magnitude of the second vector, which is 9 plus 25 is 34, square root of 34. And so I've got the cosine of theta is equal to that. So theta will be the inverse cosine of 22 divided by the square root of 20 times the square root of 34. Now, I'm not bothering to try and simplify this fraction at all because I know that it's not a cosine value that we're familiar with, so I'm going to have to use a calculator anyway to figure out what this angle is. So let's grab a calculator and make sure we're in degree mode, which I'm not. Okay. And now let's do inverse cosine, second cosine, 22 divided by, now be careful here, you need parentheses if you're going to put the individual square roots. Or I can save myself some work, and how about I combine those and just say 20 times 34 inside one radical. And that should give me my angle. 32.47 degrees approximately. 32.47. And so that's the angle between these two vectors. Obviously the shortest angle between them. So when we're looking at two vectors like this, we're finding this angle here. We're not finding the long angle all the way around. All right. Let's go back to the other question I had. Now what if the dot product winds up being 0? Well, what's going to happen in these calculations? We're going to get 0 over whatever their magnitudes are, which means this whole fraction will equal 0. When does a cosine equal 0? Oh, that's at pi over 2, 90 degrees. Which means what? Your two vectors are going to be perpendicular. So if the dot product is 0, then you know the two vectors are orthogonal or perpendicular. Or another word for that is normal. All three of those mean the same thing. So vectors are orthogonal, perpendicular, or normal. All right, let's go back and do one more example here. Oh, here it is. All right, let's find the angle between these two vectors. So once again, we start off with our formula. The cosine of theta equals u dot v. It's good to write it a few times until you really remember it. So the dot product is going to be 12 plus negative 3 times 4 is negative 12 divided by, who cares? I know I've got 0 over something, which is 0, and the cosine of 0 is, the cosine equals 0 when the angle is 90 degrees. So the angle between them is 90. So two vectors, u and v, are orthogonal, perpendicular, if and only if, I don't know how often this has come up, that's what I abbreviate IFF, if and only if the dot product is 0. What that means is it means it works both ways. So if the vectors are perpendicular, then you automatically know the dot product is 0, even if you don't know the specific components of each vector. You know that if I tell you that they're 90 degrees apart, you automatically know the dot product is 0. And the reverse is also true. If the dot product is 0, you automatically know that they're going to be perpendicular. And then finally, you wouldn't think that this would come up much, but there is a vector, the vector 0, 0, which has no length, and that's orthogonal to every other vector.